All right, let's gear up for a high-stakes microscopic mission. Our target, the genetic code of a virus. It's RNA. Over the next few minutes, we are going to see exactly how scientists pull this tiny, invisible blueprint right out of a sample. Let's dive in.
So here's the thing. Think of a virus like a microscopic vault. It's got its precious RNA locked inside, and it's surrounded by proteins, fats, all kinds of biological junk. To study it, you have to get it out, and it has to be completely pure and undamaged. So, how do you even do that?
Well, that's where our mission begins. We're going to follow the exact protocol from a QIAMP viral RNA mini-kit, and you'll see how scientists basically become molecular secret agents. They're going to break into the virus and make off with its most valuable intel, its RNA.
Okay, this whole mission breaks down into 3 phases. And phase 1, it's all about the smash and grab. We have to break everything open and capture our target before it has a chance to get away.
The objective for this first part is crystal clear. We need to lyse, burst open, the virus and pretty much any other cells in the sample. And then we've got to make sure that the viral RNA, and only the RNA, gets stuck to our special trap.
Now, this isn't just mixing stuff randomly. Every single step has a very precise purpose. That buffer AVL, it's a super powerful detergent that just demolishes the virus's protective shell. The carrier RNA, that kind of acts like a decoy, protecting our real target. Then, after a good mix and a short wait, we add ethanol. And this part is absolutely key, because it creates the perfect chemical environment for the RNA to stick to our trap in the very next step.
And this is our secret weapon for the mission, the QIAMP mini-column. Seriously, just think of it as a highly advanced molecular trap. Inside, it's got a silica membrane that, under the right conditions, which, we just created with that ethanol, has an almost magnetic attraction to RNA.
So now we pour our chemical soup right into the column and pop it in a centrifuge. Spinning it at 8,000 revolutions per minute forces all that liquid through the silica filter. All the unwanted junk, the proteins, fats, all that cellular debris, it just washes right through. But our target, the viral RNA, it gets stuck. And it gets stuck fast to that molecular trap. And just like that, our code has been captured.
All right, with the RNA captured, we're on to phase 2. But here's the problem. Our sample is still pretty messy. It's got all this microscopic gunk clinging to it. So, it's time for a deep clean.
So, the goal here is all about purification. We need to wash our silica trap, get rid of any little contaminants that might have stuck around, and leave behind nothing but pure, isolated viral RNA. The first wash uses something called buffer AW1. You can think of this as the power rinse. We add it to the column, spin it again, and this buffer washes away any of the bigger impurities that were still hanging on. The RNA, though, it stays locked right onto that filter.
That first spin was at 8,000 RPM. Pretty fast, right? Well, for the final rinse, we're going to have to crank it up a notch.
Okay, so the second wash uses buffer AW2. This is the fine-tuning clean. It's specifically designed to remove even smaller contaminants, like salts, that could totally mess with our analysis later. But what's really cool is how we spin it.
We almost doubled the speed to a whopping 14,000 RPM, and we spin it for 3 full minutes. This intense, high-speed spin literally forces out absolutely everything except our target RNA. Now, our target is clean.
And that brings us to the final and probably the most critical phase of the whole mission. The RNA is captured, it's clean, it's pure. Now we just have to get it off the trap.
We've done all the hard work, all the capturing and cleaning, so now it's time for that one final delicate step, releasing our prize from the molecular trap. To do this, we bring in a new player, buffer AVE. This buffer is basically just super sterile, salt-free water. Its chemistry is completely different from the ethanol solution we used before. It flips a switch, neutralizing the silica filter's magnetic charge, and that causes the RNA to lose its grip and just let go. We let it sit for a minute to give all the RNA time to dissolve, and then one final spin at 8,000 RPM pushes our purified RNA solution into a clean tube.
And there it is, the 2 most beautiful words in any extraction mission. Filtrate contains viral RNA. Mission accomplished.
So, we did it. We have this tiny tube with a few microliters of clear liquid in it. It might not look like much, but what we've just isolated is incredibly powerful. So why does all of this actually matter? Well, this right here is the payoff for our mission. That purified RNA is the essential starting point for so much of modern medicine and science. It's what gets put into a PCR test to diagnose a disease. It's what scientists use to sequence a new virus's entire genome to figure out how it works. And it's the fundamental building block for developing life-saving research and vaccines.
And that's really the big takeaway here. This whole intricate mission, it's a cornerstone of how we respond to health crises. Every single time a new virus emerges, you can bet that scientists are running this exact process, racing against the clock to capture its code. Which, it leaves us with one final thought. What's the next microscopic threat this powerful technique is going to help us conquer?